You're given a conductor in this shape, so let's apply a voltage to it. We'll apply a DC bias and we'll have a DC current flowing. Now let's imagine what the current density would look like inside this conductor. These lines here represent the current density, so the closer they are spaced, the greater the current density. As the conductor flares out, the current density will spread out, so it will change both in magnitude and direction. To determine the current, we have to pick a plane of observation, count how much charge goes through this plane in time t, and divide by t. We should be able to pick any plane and figure out what current is flowing. So we could pick a plane like this, a plane like this, a plane like this, a plane like this. Let's look at two planes like these two and convince ourselves that we would get the same current. Here is our conductor with the current flowing to the right, and these dots represent the charge that's flowing to the right. Let's assume every second the charges would move this distance. So 1 second, another second, another second, and so forth. So let's first look at this as our plane of observation. So in 1 second, you see 4 charges go through that plane. So we could designate the measured current as 4 charges per second. Now select this as our plane of observation. So in 1 second, we're going to have 4 charges go through. So for either plane, in 1 second, we'll have 4 charges go through it, so you would get the same current no matter how your plane cuts through your conductor. These lines represent a current density flowing to the right. These dots represent a view of the current from the edge here. This is a surface whose outward normal is in the direction of the current density, and this is the same surface, the outward normal being this red dot. So we see we have 4 lines of current density flowing through this surface. Here's a surface oriented so that its outward normal is perpendicular to the current density. This is the same surface here, so it's like taking this surface, rotating the bottom edge towards you and the top edge away. When the surface outward normal is perpendicular to the direction of current density, no current flows through the surface. Going from this surface to this surface, we rotated the outward normal 90 degrees. Now let's rotate this surface at something less than 90 degrees. So this edge comes out towards you and this edge goes into the page, but you don't rotate all the way to where you're looking edge on. So we've rotated enough so only one line of our current density goes through the surface. The amount of current going through a surface will depend on the angle between the outward normal to the surface and the current density. If our plane of observation is making an angle theta with the current density, to find the current flowing through this plane, we need to find the area of this surface right here. This surface is the projection or shadow of this surface such that the outward normal of this surface is in the direction of the current density. If this angle between the outward normal of this surface and the current density is theta, then this angle in here is also theta. So you can think of this as a right triangle where the hypotenuse is area S, and this side is the area you want to find, so it's the hypotenuse S times the cosine of theta. So the area of this plane, S cosine of theta, times the current density will be the current flowing through this plane of observation. This is just the definition of the dot product between the current density and our surface S. If this were a surface differential, part of a larger surface you're integrating over, then we'll call this ds, and now the part of the current going through our differential surface would be J dot ds. And so to get the total current, you would integrate over your surface of J dot ds. This is really very similar to what we did with Gauss's law. The only difference is this is not a closed surface, because usually finding the current, you're not looking at a closed surface.